Imagine standing on the edge of a world that's about to disappear. Not slowly, not over centuries, but in what amounts to a geological instant. It's 12,800 years ago, and Earth is finally warming up after tens of thousands of years locked in ice. Glaciers that stretched from the North Pole almost to where New York City would one day stand are melting. The planet is breathing out, relaxing, coming back to life. Then something happens, something so catastrophic that it will haunt scientific debates for the next 13,000 years. The woolly mammoths wandering across the grasslands of North America don't know they're living in the final chapter of their story. The massive ground sloths, some standing 20 feet tall when they rear up on their hind legs, have no idea their days are numbered. Saber-toothed cats, giant beavers the size of black bears, camels, horses, dire wolves. None of them know that within a few centuries they'll all be gone, vanished, extinct, just bones and memories pressed into the earth. And here's what makes this mystery so captivating, so endlessly debatable. Nobody can agree on what killed them. Was it a comet? Did something from deep space slam into Earth's atmosphere, fragmenting into thousands of pieces, igniting wildfires across an entire continent and plunging the planet back into another ice age just when things were getting better? That's what some scientists believe, and they've got evidence. Strange materials in the geological record, microscopic diamonds that only form under extreme pressure, platinum spikes, magnetic spherules, the signature of cosmic impact. Or was it something else entirely? A massive flood of glacial meltwater pouring into the North Atlantic, shutting down the ocean currents that keep Europe warm, triggering a climate catastrophe that rippled across the globe? That's another theory, and it's got its own compelling evidence. Or maybe, and this is where it gets really uncomfortable, maybe it was us. Maybe humans, spreading across the Americas for the first time, armed with sophisticated stone weapons and working in coordinated hunting groups, simply killed everything big enough to be worth hunting. Overkill. A massacre so thorough that 3/4 of North America's large mammal species disappeared forever. The truth is, we still don't know for sure, and that's what makes this story perfect for falling asleep to. Because I'm not here to give you easy answers. I'm here to walk you through one of the most fascinating, most controversial mysteries in all of paleoclimatology. If you're settling in for the night, wherever you are, leave a comment and tell me where you're watching from and what time it is. I check them all, and it's wild seeing Tokyo at sunrise, London at lunch, Los Angeles at bedtime, all exploring the same ancient mystery together. What we do know is this. Around 12,800 years ago, Earth entered a period that scientists call the Younger Dryas. Named after a small Arctic flower called Dryas octopetala that suddenly appears in the geological record across Europe, this was a climate event that should not have happened. The planet was warming, ice was melting, then suddenly, viciously, temperatures plummeted. In some regions it got as cold as it had been at the peak of the Ice Age, and this cold snap lasted not for a few years, not for a few decades, but for 1,200 years. 1,200 years of unexpected, devastating cold. To put that in perspective, that's longer than the time between Charlemagne's empire and today. Imagine if our climate suddenly shifted back to Ice Age conditions right now, and stayed that way until the year 3,200. That's what the Younger Dryas did to our ancestors. The glaciers that had been retreating started advancing again. Sea levels that had been rising stabilized, then dropped. Ecosystems that had been adapting to warmth suddenly had to adapt to cold. And something, maybe the cold, maybe something else, maybe a combination of factors we're still trying to untangle, drove dozens of species into extinction. This is the story of that vanishing world, the evidence for what happened, the theories about why it happened, and the ongoing scientific battle to understand one of the most dramatic climate events in recent geological history. We'll look at cosmic impacts and ocean currents, at ancient hunters and giant beasts, at microscopic diamonds and continent-spanning fires. Because 12,800 years ago, something ended. An entire era of Earth's history came to a close, and in the ashes of that ending our modern world began to take shape. The question is, what actually happened? Let's go back to a world you wouldn't recognize. 15,000 years ago, Earth was a fundamentally different place. Not just colder, not just different, but transformed in ways that would seem alien to modern eyes. This was the late Pleistocene, the tail end of the last great ice age, and if you could stand on what's now the coast of New York City, you wouldn't see ocean. You'd see land stretching another 100 miles out to sea, forests and grasslands where today ships navigate through deep water. The ice sheets were still there, still massive, but they were beginning their long retreat. In North America, the Laurentide ice sheet covered everything from the Arctic down to what's now New York, Chicago, and Seattle. We're not talking about snow. We're talking about ice 2 miles thick in places, so heavy it was pressing the Earth's crust down like a finger pushing into soft clay. The weight was so enormous that the land is still rebounding today, thousands of years after the ice melted. Parts of Canada are rising several millimeters per year, slowly recovering from that ancient compression. But here's what made this world spectacular. All the water locked up in ice had lowered global sea levels by nearly 400 feet. Coastlines extended far beyond their modern positions. What we call the English Channel was a river valley. You could walk from France to Britain without getting your feet wet. Indonesia was connected to mainland Asia by a subcontinent called Sunderland, larger than modern India. Australia, New Guinea and Tasmania formed a single massive landmass called Sahul. And then there was Beringia. The land bridge connecting Siberia to Alaska wasn't just some narrow strip of tundra. It was a subcontinent unto itself, 1,000 miles wide in places, a vast grassland ecosystem that supported herds beyond imagination. This was the highway that brought humanity to the Americas, but it wasn't empty. It was teeming with life, the Megafauna. That's what we call them now, but the name doesn't do them justice. These weren't just big animals. They were monsters, creatures that would make modern elephants look modest. In North America, Columbian mammoths stood 14 feet tall at the shoulder and weighed up to 10 tons. Their tusks could reach 16 feet long, massive curved weapons and tools that they used to strip bark from trees and dig through snow to reach vegetation beneath. But the mammoths weren't even the biggest things out there. American mastodons roamed the forests, browsing on leaves and branches with their peculiar cone-shaped teeth. Giant ground sloths, some weighing up to 4 tons, stood on their hind legs to reach high branches, their massive claws capable of tearing through wood and defending against predators. Some of these sloths were so large they likely had few natural enemies once they reached adulthood. Then there were the predators, short-faced bears that stood 12 feet tall on their hind legs, possibly the largest carnivorous land mammal that ever existed. They had long legs built for speed, capable of running down prey across open grasslands. Saber-toothed cats prowled the landscape, their enormous canine teeth not just for show, but precision instruments designed to deliver killing bites to the throats of massive prey. Dire wolves hunted in packs, larger and more robust than modern wolves, with bone-crushing jaws that could snap the leg bones of bison and horses. American lions, a quarter larger than modern African lions, ranged across the continent. Giant beavers the size of black bears built dams in rivers and lakes. Armored glyptodons, looking like Volkswagen-sized armadillos, grazed peacefully with shells too tough for most predators to penetrate. The skies weren't empty either. Teratons, condor-like birds with 12-foot wingspans, soared overhead, watching for carrion or perhaps small prey they could snatch and carry away. This wasn't some impoverished ecosystem struggling at the edge of extinction. This was abundance. The grasslands and parklands at the edge of the ice sheets were incredibly productive, nourished by mineral-rich meltwater and supporting plant growth that could feed massive populations of herbivores. The cold climate actually helped. Less evaporation meant more available water. Seasonal freezing preserved organic matter instead of letting it rot, creating rich soils that exploded with growth during brief but intense summers. Europe had its own megafauna assemblage. Woolly mammoths smaller than their American cousins, but perfectly adapted to the extreme cold, with their thick coats and small ears. Cave bears that weighed up to a ton and competed with humans for shelter in limestone caverns. Woolly rhinoceros with 2 horns and dense fur built like living tanks. Giant elk with antlers spanning 12 feet, the largest antlers ever evolved, so massive that males probably shed them every year just to survive winter when food was scarce. And everywhere there were humans. Not many, not yet, but they were there, and they were getting better at being human with each passing generation. In North America they were called the Clovis people, named after distinctive spear points first discovered near Clovis, New Mexico. But they weren't just one tribe or one group. The name represents technological tradition, a way of making tools that spread across the continent with remarkable speed. Clovis points are works of art, carefully crafted from high-quality stone using techniques that modern flint knappers struggle to replicate. These weren't crude stone chips. They were precision instruments, symmetrical, aerodynamic, with fluted channels running up both faces that allowed them to be hafted securely to spear shafts. The Clovis people were sophisticated hunters. They understood animal behavior, migration patterns, seasonal movements. They knew how to work cooperatively, how to coordinate group hunts that could bring down animals 10 times their size. Archaeological sites show mammoth kills where multiple animals were taken at once, butchered systematically, with every useful part carried away or processed on site. These weren't desperate scavengers. These were confident, competent people at the top of their game. They had fire, and they knew how to use it. Not just for warmth and cooking, but as a tool for landscape management, for driving game, for creating the kind of open grasslands that supported the megafauna herds. They made sophisticated clothing from animal hides, sewn with bone needles using sinew thread. They created tools from bone, antler, and ivory, when stone wouldn't do the job. They transported high-quality stone across hundreds of miles, indicating trade networks or seasonal movements over vast territories, and the world was warming. This is crucial. Around 15,000 years ago, Earth's climate began one of its periodic shifts from glacial to interglacial conditions. The massive ice sheets that had covered the northern continents were melting. Not quickly by human standards, but inexorably, year by year, century by century. Summers were getting slightly longer, winters slightly milder. Grasslands were expanding as the climate became less harsh. The megafauna were thriving in this transition period, moving north as new territories opened up following the retreating ice. Everything was connected. The mammoths browsed on grasslands and spread seeds in their dung, helping vegetation colonize newly ice-free ground. Their feeding created open meadows that supported bison, horses, and camels. The predators followed the herds, maintaining population balances, preventing any single species from dominating. Humans hunted carefully, taking what they needed but not destroying the resource base they depended on. Scavengers cleaned up the remains, recycling nutrients back into the ecosystem. It was a web of relationships refined over tens of thousands of years, and it should have continued. Based on Earth's orbital cycles and previous interglacial periods, the warming should have proceeded smoothly for thousands of years. The ice should have gradually retreated, sea levels should have slowly risen, ecosystems should have shifted northward at a pace that allowed species to adapt. Humans should have continued their expansion, their populations growing gradually as their territories expanded with the warming climate. That's what should have happened. That's what the pattern of previous ice ages suggested would happen. But right at the moment when everything seemed poised for a smooth transition into a warmer world, something went catastrophically wrong. The warming stopped, then it reversed, and when it was over, 2/3 of the megafauna species in North America would be gone forever. Picture yourself standing on a grassy plain in what will one day be called France. It's 13,000 years ago, and the world has been warming for thousands of years. The massive ice sheets that once covered half of Europe are finally retreating. Your ancestors have been watching this happen for generations. Every year, the glaciers pull back a little farther north. Every spring, new land appears where ice had stood for millennia. The herds of horses, bison and reindeer are thriving. Rivers run full of meltwater. Forests are beginning to creep back into territories that haven't seen trees in 50,000 years. Life is getting easier. Your people are expanding, developing new technologies, creating art that will still be admired 15,000 years in the future. The Ice Age is ending. Everyone can feel it. The long winter of humanity is finally coming to an end. And then, almost overnight in geological terms, everything changes. The warming stops, not gradually, not over centuries, but abruptly. Within a single human lifetime, maybe within a single generation, the world plunges back into winter. Temperatures drop. In some regions of the northern hemisphere, the thermometer crashes by up to 10 degrees Celsius. That might not sound like much until you realize that's the difference between the climate of England and the climate of northern Scandinavia. The difference between forests and tundra. The difference between abundance and survival mode. The glaciers that had been retreating for thousands of years stop their withdrawal. In some places they begin advancing again. Lakes that had been ice-free for centuries freeze solid. Plants that had colonized newly exposed ground die off, replaced by hardy tundra species that can survive the renewed cold. The animals follow. Species that had been thriving in the warming world find themselves struggling again, pushed back into smaller refuges, competing for dwindling resources. This wasn't supposed to happen. Earth's climate had been on a steady warming trend for over 5,000 years. All the evidence suggested the Ice Age was ending, but something had broken Earth's thermostat, and now the planet was plunging back toward full glacial conditions. Scientists call this period the Younger Dryas. The name comes from a small Arctic flower, Dryas octopetala, with 8 delicate white petals and leaves that hug close to the ground. It's a plant that thrives in the coldest conditions, flourishing on windswept tundra, where almost nothing else can survive. When geologists analysing ancient sediment cores and pollen records found massive spikes in Dryas pollen around 12,800 years ago, they knew something dramatic had happened. This flower, which had been rare in European sediments during the warming period, suddenly dominated the landscape again. The cold had returned. The Younger Dryas lasted roughly 1,200 years, from about 12,800 to 11,600 years ago. But those numbers, precise as they sound, don't capture the violence of the transition. The archaeological and geological evidence suggests the cooling didn't ease in gradually over centuries. It happened fast, catastrophically fast. Ice cores from Greenland tell the story most clearly. Scientists drilling into ancient ice can read climate history year by year, sometimes season by season, in the layers of frozen snow that have accumulated over millennia. The chemical composition of each layer, the types of dust and pollen trapped in the ice, the ratio of different oxygen isotopes in the water molecules themselves, All these details create a climate record more precise than any written history. And what those ice cores show is startling. The transition into the younger Dryas happened over decades at most, possibly even faster. Some researchers think temperatures in Greenland might have dropped by several degrees within a single decade. That's not climate change as we usually think of it. That's climate collapse. Imagine experiencing that. You're a hunter following herds across the plains of Ice Age Europe. The weather has been relatively stable your entire life. Winters are cold but manageable. Springs bring warmth and renewal. Summers are brief but productive. Your people have adapted to this rhythm, developed seasonal strategies that have worked for generations. Then, over the course of just 10 years, the pattern breaks. Winters start lasting longer. Springs arrive late, if they arrive at all. Summer warmth becomes uncertain, unreliable. The herds you depend on begin migrating differently, or not at all. Plant foods that had been staples become scarce. The old strategies don't work anymore, and you have no idea if this is temporary or permanent. No concept of climate science to tell you what's happening. No weather forecasts, no historical records to consult. Just the terrifying realization that the world is changing faster than your people can adapt. The geological evidence for this rapid transition shows up everywhere, not just in ice cores. Lake sediments from across Europe and North America show dramatic shifts in the types of microscopic organisms living in the water. Species that prefer warmer conditions vanish suddenly from the record, replaced by cold water specialists. Tree rings from ancient stumps preserved in peat bogs show years of stunted growth starting exactly at the younger Dryas boundary. Some trees that had been growing for centuries simply stopped growing altogether, entering a kind of suspended animation as they waited for better conditions that wouldn't arrive for over 1,000 years. Pollen records paint an even more detailed picture. As temperatures dropped, forests retreated rapidly southward. Oak and elm pollen, which had been increasing in northern sediments during the warming period, virtually disappears at the younger Dryas boundary, replaced by pine, then by tundra grasses and sedges, and finally by that telltale Dryas flower. It's like watching a time-lapse video of the ecosystem rewinding, undoing thousands of years of warming in just decades. The temperature drop wasn't uniform across the planet. The northern hemisphere, especially regions around the North Atlantic, got hit hardest. Temperature reconstructions suggest drops of 8 to 10 degrees Celsius in Greenland and northern Europe. Britain, which had been warming nicely, plunged back into near-glacial conditions. Parts of North America saw similar dramatic cooling. But here's where it gets interesting. The southern hemisphere didn't cool nearly as much. Some regions actually warmed slightly during the younger Dryas. This asymmetry is crucial because it tells us something important about the mechanism behind the cooling. Whatever caused the younger Dryas, it wasn't a global phenomenon like a drop in solar radiation or a massive volcanic eruption putting dust into the upper atmosphere. Those would have affected both hemispheres roughly equally. No, this was something that specifically disrupted the climate of the northern hemisphere, something that could explain why temperatures around the North Atlantic crashed, while the rest of the world remained relatively stable. The puzzle deepened when scientists realized just how abrupt the end of the younger Dryas was. The ice cores show that the warming that finally ended this cold snap was even more dramatic than the cooling that began it. In some locations, temperatures might have risen by 10 degrees Celsius or more within just a few years, perhaps within months in some regions. Think about that for a moment. The entire 1,200-year cold period was bookended by two catastrophic climate transitions. First, a plunge into cold that happened within decades. Then, over a millennium later, a surge back to warming that happened even faster. Earth's climate was behaving less like a gradually adjusting thermostat, and more like a light switch being flicked on and off. These aren't the timescales climatologists expect for natural climate variation. Ice ages are supposed to come and go over tens of thousands of years, driven by slow changes in Earth's orbit and the wobble of its rotational axis. Even shorter climate fluctuations typically take centuries to develop. But the younger Dryas developed in decades and ended in years. Something had triggered a rapid, catastrophic change in the way Earth's climate system operates. Some kind of threshold had been crossed, flipping the system from one state to another almost instantaneously on geological timescales. Scientists first identified the younger Dryas in the 1930s, but for decades it remained a geological curiosity, a strange blip in the climate record that nobody could quite explain. Early theories suggested it might be related to changes in solar radiation or volcanic activity. Maybe a massive eruption had temporarily cooled the planet. But the geological record didn't support this. There's no evidence of catastrophic volcanic activity at the start of the younger Dryas. Others wondered if it might be connected to changes in Earth's orbit. The Milankovitch cycles that drive ice ages operate on timescales of tens of thousands of years, but maybe some shorter-term orbital variation could explain a 1,200-year cold snap. This theory didn't hold up either. The astronomical calculations showed nothing unusual happening around 12,800 years ago. The real breakthrough came in the 1980s, when oceanographers studying ocean currents began to understand how quickly the circulation patterns in the North Atlantic could change. They discovered that relatively small perturbations in ocean salinity or temperature could potentially shut down major current systems. And when those currents shut down, they could drag entire hemispheres into renewed ice age conditions. But that just pushed the mystery back one level. What could cause such a dramatic perturbation? What could dump enough fresh water into the North Atlantic to disrupt ocean circulation on such a massive scale? The ice sheets were melting, sure, but they'd been melting gradually for thousands of years. Why would the meltwater suddenly cause problems at 12,800 years ago specifically? The sediment layers from the younger Dryas boundary began yielding strange clues. Black layers rich in carbon, suggesting massive wildfires, microscopic diamonds that form only under extreme temperature and pressure, elevated levels of rare elements like platinum and iridium that are more common in space than on Earth's surface, tiny magnetic spherules that look like they formed in the intense heat of an impact event. And suddenly, what had seemed like a straightforward climate puzzle was becoming something else entirely. Maybe Earth's thermostat hadn't just broken. Maybe something had smashed it. So, Earth's climate had just collapsed into 1,300 years of brutal cold. Glaciers were advancing, megafauna were dying, human populations across North America were struggling to survive, and everyone assumed it was just another climate shift, another natural swing in Earth's complex weather systems. Then, in 2007, a team led by nuclear physicist Richard Firestone proposed something nobody was expecting. What if it wasn't just climate change? What if something had hit us? Not a metaphor, not a gradual environmental shift, something from space, something that struck North America with enough force to change the entire planet's climate in a matter of years, maybe even months. The younger Dryas impact hypothesis wasn't suggesting a gentle cosmic visitor. It proposed that around 12,800 years ago Earth encountered the debris field of a fragmenting comet. Multiple chunks of ice and rock, some possibly several kilometers across, either slammed into the ice sheets covering North America or exploded in the atmosphere above them. The result would have been catastrophic. Immediate devastation across the impact zones, massive wildfires spreading across the continent, enough debris thrown into the atmosphere to darken skies for months or years, and most significantly, enough energy dumped into the North American ice sheets to trigger rapid melting, flooding the oceans with cold fresh water and disrupting the currents that kept the Northern Hemisphere warm. This wasn't a fringe theory proposed by conspiracy theorists or amateur researchers. Firestone and his colleagues were serious scientists publishing in serious journals. They had evidence, or at least they claimed they did. The first piece of evidence was subtle but intriguing. Nanodiamonds. These are microscopic diamond crystals that form only under conditions of extreme pressure and temperature, the kind of pressure and temperature you get during meteor impacts or nuclear explosions. Firestone's team reported finding concentrations of nanodiamonds in sediment layers dating to exactly 12,800 years ago, not just at one site, but at multiple locations across North America and Europe. These weren't random diamonds weathered out of ancient geological formations. They appeared suddenly in the sediment record, right at the boundary between the Clovis period and the Younger Dryas, right where you'd expect to find evidence of a cosmic impact. Then there were the magnetic spherules. These are tiny balls of iron and other metals that form when rock is vaporized by intense heat and then condenses in the atmosphere. You find them at known impact sites like the Chicxulub crater in Mexico, where the dinosaur-killing asteroid struck 66 million years ago. Firestone's team found similar spherules in the same 12,800-year-old sediment layer that contained the nanodiamonds. The microscopic structure of these spherules suggested they had been subjected to temperatures exceeding 2,000 degrees Celsius. That's hot enough to melt rock, hot enough to vaporize it. But the most compelling evidence, at least at first, was platinum. Platinum is rare on Earth's surface. Most of it is locked deep in the planet's core, or it arrived here on meteorites after Earth's crust had solidified. When you find sudden spikes in platinum concentration in sediment layers, it usually means something from space delivered it. The team reported finding platinum anomalies at the Younger Dryas boundary layer across dozens of sites. Not huge amounts, but statistically significant increases that appeared suddenly and then declined just as quickly. The pattern looked exactly like what you'd expect from an extraterrestrial impact. And there was more. At sites across North America, archaeologists had long noted something called the black mat, a layer of dark sediment rich in carbon and organic material that appeared right at the boundary between the Clovis period and what came after. Nobody had been quite sure what caused it. Some thought it was just increased plant growth during a wet period. Others suggested it represented forest fire debris. The impact hypothesis offered a different explanation. What if the black mat represented the remains of massive continent-wide wildfires triggered by the impact event? If fragments of a comet had exploded in the atmosphere over North America, the airburst would have released thermal radiation intense enough to ignite forests across thousands of square miles. The resulting firestorm would have burned across the continent for weeks or months, consuming everything combustible. The ash and charcoal from these fires would have settled into a distinct layer, creating exactly the kind of black mat observed in the archaeological record. The scenario they proposed was apocalyptic. Picture this. It's a normal day 12,800 years ago. Clovis hunters are tracking mammoth herds across the Great Plains. Families are gathering around fires in temporary camps. Children are learning to knap stone tools from their elders. Then, without warning, the sky lights up. Multiple fireballs, each one brighter than 1,000 suns, streak across the heavens. Some impact directly on the massive ice sheets covering Canada. Others explode in the atmosphere, releasing energy equivalent to thousands of nuclear weapons. The thermal pulse ignites everything it touches. Forests burst into flame from horizon to horizon. Animals caught in the open are incinerated instantly. Those in sheltered valleys might survive the initial blast only to suffocate in the smoke and heat that follows. The ice sheets absorb devastating amounts of energy. Within hours, meltwater is cascading off the glaciers in unprecedented volumes. Within days, massive floods are roaring south, carving new channels and drowning river valleys. Within weeks, enough cold fresh water has poured into the North Atlantic to disrupt ocean currents, shutting down the heat conveyor belt that keeps Europe and eastern North America warm. And the humans, the Clovis people who'd been thriving just moments before, those near the impact zones are simply gone, vaporized or buried under megatons of debris. Those farther away face a rapidly collapsing world. The megafauna they depended on are dying from the fires, the climate shift and the sudden loss of food plants. Their sophisticated hunting culture, so perfectly adapted to late Ice Age conditions, becomes useless in a matter of years. The hypothesis offered an explanation for one of the most puzzling archaeological mysteries in North American prehistory. Why did Clovis culture disappear so suddenly? Why do we stop finding their distinctive spear points right at the Younger Dryas boundary? Traditional explanations suggested gradual cultural evolution or climate adaptation, but the archaeological record didn't show gradual change. It showed abrupt disappearance followed by a long gap, and then the emergence of different tool traditions. An impact event could explain this. If the catastrophe killed a significant percentage of the North American population and scattered the survivors, you'd expect to see exactly what the archaeology shows. Sudden disappearance of the old culture, followed by a period of reduced population and technological simplification, and then eventually the emergence of new traditions among the descendants of survivors. The scale of the proposed event was staggering. The researchers suggested the impacting object or objects might have delivered energy equivalent to millions of megatons of TNT. For comparison, the largest nuclear weapon ever tested, the Soviet Tsar bomber, released about 50 megatons. The asteroid that killed the dinosaurs released energy equivalent to about 100 million megatons. The Younger Dryas impactor would have fallen somewhere between these extremes. Not large enough to cause a mass extinction, but more than sufficient to devastate a continent and trigger global climate change. But here's where the hypothesis gets even more interesting. Some versions suggested the impact might not have been a single massive strike, but rather multiple smaller impacts or airbursts scattered across North America and possibly Europe and Asia. This would explain why researchers couldn't find a single giant crater matching the proposed date. The comet might have been fragmenting as it approached Earth, breaking up into dozens or hundreds of pieces that struck across a wide area. This scenario actually has precedent. In 1994, astronomers watched as Comet Shoemaker-Levy 9 broke into more than 20 fragments before striking Jupiter. The impacts created visible scars in Jupiter's atmosphere larger than Earth. If a similar fragmented comet had struck our planet, each fragment would have caused its own localized catastrophe, but the combined effect would have been devastating. The airburst scenario was particularly appealing because it solves several problems. Airbursts don't leave impact craters, which would explain why researchers haven't found a smoking gun crater dating to the Younger Dryas boundary. But they do generate massive thermal radiation, shock waves, and can scatter exotic materials across wide areas, all of which match the reported evidence. The most famous recent airburst occurred in 1908 in Tunguska, Siberia. Something, probably a small asteroid or comet fragment, exploded about 5 to 10 kilometers above the ground. The explosion released energy equivalent to 10 to 15 megatons of TNT. It flattened 2,000 square kilometers of forest. Trees were knocked down in radial patterns extending 20 kilometers from the blast center. If you'd been standing directly under that explosion, you would have been incinerated. But it left no crater, just a zone of destruction and scattered debris. Now imagine not one Tunguska event, but dozens, maybe hundreds, scattered across North America, some exploding over the ice sheets, others over forests, a few possibly striking the ground in regions that were then under ice or ocean. The combined effect would have been exactly what the impact hypothesis proposed. Widespread fires, rapid climate shift, population collapse, and a boundary layer full of exotic materials marking the moment everything changed. For the Clovis people, If this scenario is correct, it would have been the end of their world. Not slow, not gradual, not something they could adapt to over generations. Just sudden, complete catastrophe. One day they're the most successful culture in the Americas. The next day their world is burning. But was any of this actually true? Did a comet really fragment over North America 12,800 years ago? The hypothesis was compelling, dramatic, and seemed to explain multiple mysteries at once. But extraordinary claims require extraordinary evidence, and almost immediately other scientists began asking uncomfortable questions about the evidence Firestone's team had presented. The debate that followed would become one of the most contentious in recent archaeological and geological history. So, you're standing in a laboratory in 2007. A researcher named Alan West is examining sediment samples from an archaeological site in Arizona. Nothing particularly unusual about that. Archaeologists examine dirt all the time. It's basically their job description. But when West looks at the samples under an electron microscope, he sees something that shouldn't be there. Tiny diamonds, not the kind you'd put on a ring. These are nanodiamonds, microscopic crystals barely a few nanometers across, and they're sitting in a layer of sediment that dates to exactly 12,800 years ago, the precise moment when the younger Dryas began. Nanodiamonds are interesting things. They don't form under normal conditions. You need extreme pressures and temperatures, the kind you get deep inside the Earth over millions of years, or the kind you get in a massive explosion, like a nuclear blast or an asteroid impact. Finding them in surface sediments is like finding a piece of the sun in your backyard. It suggests something very unusual happened. West and his colleagues started looking at more samples, not just from Arizona, but from sites across North America. And they kept finding the same thing. A thin layer of sediment, always dating to 12,800 years ago, packed with nanodiamonds. The layer showed up in Pennsylvania, in South Carolina, in California, even in Belgium and Syria. It was like someone had drawn a line across the Northern Hemisphere, marking the exact moment when everything changed. But nanodiamonds weren't the only oddity in this mysterious layer. The sediments also contained spherules, tiny balls of melted rock and metal that had been flash-heated to extreme temperatures, then rapidly cooled. The magnetic spherules showed signs of having been exposed to temperatures exceeding 2,200 degrees Celsius. That's hotter than most volcanoes can produce. The kind of heat you'd associate with an impact event, when a cosmic object slams into Earth at tens of thousands of miles per hour, converting all its kinetic energy into thermal energy in a fraction of a second. Then there was the carbon. The sediment layer contained massive amounts of microscopic charcoal particles and carbon spherules, evidence of widespread burning. Not just local fires, but conflagrations that seem to have swept across entire continents. When researchers analysed the carbon particles, they found they came from a variety of plant species, all burned simultaneously. This wasn't natural wildfire progression, where fires spread gradually from one ecosystem to another. This looked like something had ignited vast areas all at once. The really compelling evidence came from Greenland. In 2013, a team of scientists analysing ice cores from the Greenland ice sheet found something remarkable. At the depth corresponding to 12,800 years ago, platinum concentrations suddenly spiked. Not just a little increase, but a dramatic spike, platinum levels jumping to 3 times normal background levels. The spike appeared in multiple ice cores from different locations, ruling out contamination or local anomalies. Platinum is rare on Earth's surface. Most of it is locked away in the planet's core, having sunk there billions of years ago when the Earth was still molten. But platinum is relatively common in asteroids and comets. When these objects strike Earth, they deliver a sudden dose of platinum and related elements like iridium to the surface. It's the same signature scientists used to identify the asteroid impact that killed the dinosaurs 66 million years ago. Finding a platinum spike at exactly the moment the younger Dryas began seemed like smoking gun evidence for an impact. The Greenland cores revealed something else too. Above the platinum spike, the ice showed evidence of abrupt cooling. Within just a few years, temperatures in Greenland had dropped by 15 degrees Celsius. The ice went from showing signs of relatively mild conditions to indicating full glacial cold. The timing was perfect. First the platinum spike, then the temperature drop, exactly as you'd expect if an impact had triggered the climate crisis. But the most dramatic discovery was still to come. In 2018, researchers announced they'd found a massive impact crater buried beneath the Hiawatha Glacier in northwest Greenland. The crater is 31 kilometers across, big enough to have been created by an iron asteroid roughly a kilometer in diameter. When the team examined ice samples from near the crater, they found impact debris, melted rock that had been blasted into the ice by the force of the collision. Initial dating suggested the crater might be exactly the right age, 12,800 years old, the same age as the nanodiamonds, the spherals, the platinum spike, and the beginning of the younger Dryas. Imagine what that impact would have looked like. An asteroid, maybe a kilometer across, maybe a fragment of a larger comet that had broken up as it approached Earth, screaming through the atmosphere at 20 kilometers per second. The air in front of it would have compressed so violently it turned to plasma, creating a fireball that lit up the sky brighter than the sun. People hundreds of miles away would have seen it, a second sun rising in the north, growing brighter by the second, then the impact. The asteroid would have punched through the ice sheet like it wasn't there, vaporizing hundreds of cubic kilometers of ice in an instant. The energy release would have been equivalent to billions of tons of TNT, enough to create an earthquake that could be felt across the entire continent. The shock wave would have flattened forests for hundreds of miles in every direction. Anyone close enough to see the impact would have died instantly, vaporized by the thermal pulse or crushed by the blast wave. But the immediate destruction would have been just the beginning. The impact would have blasted billions of tons of rock, ice, and vaporized material into the upper atmosphere. Some of this material would have been thrown so high it reached orbital velocity, spreading around the planet before raining back down as meteoric debris. These fragments, many of them still burning from atmospheric re-entry, would have ignited fires wherever they landed. Within hours, fires could have been burning across North America, Europe, and Asia. The evidence for these fires is written in the sediment record. That charcoal-rich layer at 12,800 years ago contained something called carbonaceous spherules, tiny balls of carbon that form when organic material is flash-heated to extreme temperatures. The spherules show signs of having been created at temperatures between 2,200 and 2,400 degrees Celsius. That's not normal wildfire temperature. That's the temperature you get when vaporized rock condenses in the upper atmosphere and falls back to Earth as burning droplets. The fire evidence isn't limited to North America either. Archaeological sites across Europe show a layer of ash and charcoal dating to the same period. In Syria, a site called Abu Huraira shows clear evidence of massive burning at exactly 12,800 years ago. The site contains melt glass, silica, that had been heated so intensely it melted and fused together, creating glass-like structures embedded in building materials. The temperatures required to create this melt glass exceed 1,700 degrees Celsius. Something extraordinary had happened here. The geographic spread of the evidence is what makes it so compelling. We're not talking about isolated anomalies. We're talking about a layer of unusual materials that appears across multiple continents, always at the same time, always showing the same characteristics. Nanodiamonds in North America, Europe, and the Middle East. Platinum spikes in Greenland ice cores. magnetic spherules from Arizona to Belgium, evidence of massive fires from California to Syria. It's like finding the same fingerprint at crime scenes spread across half the planet. Some researchers have argued the impact might not have been a single asteroid but a shower of fragments from a disintegrating comet. Comets are fragile things, loosely bound collections of ice and rock held together by gravity. When they get close to the sun or pass near a large planet, tidal forces can tear them apart, creating swarms of fragments that follow similar orbits. If Earth passed through such a swarm 12,800 years ago, we could have experienced multiple impacts over a period of hours or days. This would explain some puzzling features of the evidence: why the geographic spread of impact materials is so wide, why some sites show more intense heating than others, why the archaeological record suggests not just one catastrophe, but a series of disasters unfolding over a short period. Maybe it wasn't one impact, but dozens or hundreds, fragments ranging from house-sized boulders to mountain-sized asteroids, all striking different parts of the northern hemisphere over the course of a few terrifying days. The Hiawatha crater might have been created by the largest fragment, a kilometre-wide asteroid carrying most of the comet's mass. But smaller pieces could have struck elsewhere, in the oceans, in remote areas where their craters have been eroded away or remain undiscovered. Each impact would have added its own contribution to the catastrophe. More fires, more atmospheric dust, more disruption to global climate systems. But here's where the story gets complicated. Because as compelling as this evidence seems, it's far from universally accepted. For every researcher who looks at the nanodiamonds and platinum spikes and sees proof of an impact, there's another who sees something else entirely. Natural processes that could produce similar results without requiring a cosmic catastrophe. The debate over what really happened at the start of the Younger Dryas isn't over. In many ways, it's only just beginning. But here's where the story gets complicated. Because for every piece of evidence supporting the impact hypothesis, there's a scientist somewhere with a different explanation, and they've got data too. The scientific response to the Younger Dryas impact theory wasn't subtle. Within months of Firestone's team publishing their findings, laboratories around the world started trying to replicate their results. And that's when things started falling apart. First came the nanodiamonds. Remember those microscopic crystals that supposedly could only form under the extreme pressures of an impact? Multiple independent teams went to the exact same sites where Firestone's group had found them. They collected samples using identical methods. They analysed them with the same equipment, and they found nothing. No nanodiamonds, no impact spherules, no evidence whatsoever of cosmic catastrophe. At first, this might have been dismissed as a sampling problem. Maybe Firestone's team just got lucky and found the only spots where the evidence survived. But then more teams failed to replicate the findings. Then more. Eventually, over a dozen independent studies had searched for the impact signature and come up empty. That's not a sampling problem. That's a reproducibility crisis. But it gets worse. Some labs did find nanodiamonds in the Younger Dryas boundary layer. They also found them in layers above and below the boundary, and in layers from completely different time periods. Turns out nanodiamonds aren't that rare. They form in forest fires. They show up in volcanic eruptions. They can even form in the soil through normal geological processes. Finding nanodiamonds in a sediment layer doesn't mean a comet hit. It just means something burned or got compressed. The platinum spike ran into similar problems. Initial studies showed dramatic increases in platinum concentrations right at the Younger Dryas boundary. But when other researchers looked at the same sites with better analytical techniques, the spike disappeared. What had looked like an anomaly was actually just normal background variation, amplified by small sample sizes and selective reporting. This is how science works, by the way. It's messy, it's argumentative, it's supposed to be. The first team publishes exciting findings. Other teams try to verify them. When verification fails, you go back and figure out what went wrong. Maybe the original measurements were contaminated. Maybe the sampling method introduced bias. Maybe the statistical analysis was flawed. Or maybe, just maybe, the exciting finding wasn't real. The charcoal evidence posed its own problems. Yes, there's widespread evidence of burning across North America at the start of the Younger Dryas, but there's also evidence of burning in dozens of other periods throughout the last 100,000 years. Climate changes cause fires. Droughts cause fires. Lightning causes fires. Humans cause fires. Finding evidence of widespread burning doesn't tell you what caused the burning. Several research teams pointed out something crucial. The peak in charcoal deposits doesn't actually align precisely with the Younger Dryas boundary. In many locations, the increase in burning starts hundreds of years before the cooling begins. In others, it continues for thousands of years after. If a comet impact caused the fires, you'd expect synchronicity. Everything burning at once, precisely at the moment of impact. Instead, you see a complex pattern of fires spread across centuries, which looks a lot more like climate-driven environmental change than cosmic catastrophe. Then there's the crater problem, or rather, the lack of crater problem. If something big enough to cause a global catastrophe hit Earth 12,800 years ago, it should have left a mark. And we're pretty good at finding impact craters. We've identified hundreds of them, from tiny depressions barely visible on the landscape to massive scars like Chicxulub, the asteroid impact that killed the dinosaurs. So where's the Younger Dryas crater? The impact hypothesis proponents have offered various explanations. Maybe it hit the ice sheet and the evidence melted away. Maybe it exploded in the atmosphere before impact, like the Tunguska event in 1908. Maybe it broke into dozens of smaller pieces that left scattered craters we haven't found yet. But each of these explanations creates new problems. An ice sheet impact large enough to trigger global cooling should still leave geological evidence. Shocked quartz from the bedrock, disturbed sediments in a circular pattern, something. An atmospheric explosion wouldn't produce nanodiamonds or spherules. Multiple impacts should show up as multiple distinct layers in the geological record, not a single boundary. Some researchers propose that a crater-like structure under Greenland's ice sheet might be the smoking gun. The Hiawatha crater, discovered using radar surveys, shows all the features of an impact site. But when geologists dated the ice above it, they found it was either much older than the Younger Dryas, maybe 58,000 years old, or possibly even younger, less than 10,000 years old. Either way, it doesn't align with the timing they needed. The timeline itself became a major source of controversy. When you look closely at the dating of all this supposed impact evidence, it starts to blur. The platinum spike in some locations dates to 12,950 years ago. In others, 12,700 years ago. The nanodiamond layer varies by similar margins. The charcoal peaks are spread across several centuries. Now, you might think a few hundred years doesn't matter when you're talking about events 13,000 years ago, but it matters enormously. If a comet hit Earth, all the evidence should date to exactly the same moment. The fact that the evidence is smeared across centuries suggests something else is going on. Something that happened gradually, not catastrophically. Geologists proposed alternative explanations for basically every piece of evidence. The magnetic spherules could have formed from industrial contamination, particles from early iron smelting, or even modern pollution working their way down into older sediments. The supposed cosmic materials might actually be volcanic. The Younger Dryas began during a period of increased volcanic activity, and volcanic eruptions can produce many of the same signatures as impacts. Ash spherules, trace metals, even nanodiamonds. The meltwater flooding, which some impact proponents claimed was triggered by the comet, could be explained much more simply by the natural dynamics of ice sheet collapse. No impact required, just regular ice age physics, ice dams form, ice dams break, floods happen. It had happened before the Younger Dryas. It happened during the Younger Dryas. It happened after. By the mid-2000s, the scientific community's position had solidified. Most researchers remained deeply skeptical of the impact hypothesis. Major review papers examining all the evidence concluded the proposed impact signatures weren't reproducible, weren't unique to impacts, or weren't actually synchronous with the Younger Dryas boundary. Professional societies issued cautious statements acknowledging the hypothesis was interesting but unsupported by the current evidence. But here's what makes this story fascinating. The impact proponents didn't give up. They kept looking, kept refining their evidence, kept publishing new findings. Some of their later work was more convincing than the initial studies. They found evidence they claimed couldn't be explained away by contamination or volcanism. They developed new dating techniques that they argued proved the synchronicity of the impact markers. The debate became increasingly technical. Arguments about statistical methods, laboratory protocols, sampling strategies, the kind of details that make most people's eyes glaze over but are absolutely crucial to determining what actually happened. Because that's how science resolves controversial questions, not through dramatic breakthroughs, but through painstaking accumulation of evidence, replications, reanalyses, and eventually consensus. What's interesting is that both sides in this debate agree on the fundamental observations. Yes, the megafauna went extinct. Yes, the Clovis culture disappeared. Yes, the climate changed dramatically. Yes, there's evidence of widespread fires. The disagreement isn't about whether these things happened. It's about why they happened and whether a single catastrophic event can explain them all. The critics argue that invoking a comet impact is unnecessary. The climate change alone, driven by changes in ocean circulation, can explain the extinctions and cultural disruptions. The fires can be explained by climate-driven droughts. The unusual minerals can be explained by volcanism or contamination. You don't need a cosmic catastrophe when terrestrial processes work just fine. This principle, that simpler explanations should be preferred when they fit the evidence equally well, goes back to the medieval philosopher William of Ockham. Scientists call it Occam's razor. Don't multiply causes beyond necessity. If you can explain the Younger Dryas with known climate processes, why add a comet? But the impact proponents have a counter-argument. Sometimes extraordinary events require extraordinary explanations. The dinosaur extinction required an asteroid impact. Scientists initially resisted that idea too, proposing volcanism, climate change, disease. It took decades of evidence accumulation before the impact theory was accepted. Maybe the Younger Dryas is similar. Maybe future research will prove the skeptics wrong. And that's where the debate stands today, unresolved. Both sides publishing papers, both sides claiming the evidence supports their interpretation, both sides pointing out flaws in the other's methodology. This isn't a failure of science. It's science working exactly as designed, testing ideas, demanding evidence, refusing to accept conclusions until they're proven beyond reasonable doubt. The controversy has actually been productive. It's driven researchers to develop better dating methods, more sensitive analytical techniques, more rigorous sampling protocols. It's forced everyone to think more carefully about what evidence would definitively prove or disprove an impact. It's led to discoveries about Younger Dryas climate dynamics that wouldn't have been made otherwise. But for the question that started all this, whether a comet caused the Younger Dryas catastrophe, the answer from the scientific mainstream remains decidedly skeptical. Possible? Maybe. Proven? Not even close. The Younger Dryas impact theory says something in the sky went wrong. The meltwater pulse theory says something in the water went wrong. Same cold snap, same mysterious climate crash. But instead of fire raining from above, this version of the story begins in silence, deep inside a wall of ice. Picture North America at the end of the last ice age. Not the continent, you know. Almost half of it is buried under a sheet of ice so thick it crushes mountains. The Laurentide ice sheet, a frozen shield stretching from the Arctic down into what is now the northern United States. To the west, another wall of ice, the Cordilleran ice sheet, clings to the spine of the Rockies. Between and beneath these frozen giants, the melt has already begun. Summer sun chews at the ice margins. Glaciers creak and groan. Rivers pour out from blue tunnels at the ice front, loaded with silt and gravel, spreading out into vast braided channels that look almost alive from above. But not all that meltwater escapes to the sea. Some of it pools. Trapped behind ridges of ice, rock, and frozen soil, gigantic inland seas form. Glacial lakes so large they swallow horizons. The greatest of these was Lake Agassiz. If you stood on its shore 13,000 years ago, it would feel like standing on the edge of an ocean. Wind driving waves into the ice-dammed coast. Icebergs breaking off and drifting under grey skies. The opposite shore invisible beyond the curve of the water. This was not a lake in any ordinary sense. At its full extent, Lake Agassiz covered an area larger than all the Great Lakes combined, larger than modern Germany or France. And it was being held back by a dam made not of concrete and rebar, but of ice. That's the heart of the meltwater pulse theory. You don't need a comet if you already have a loaded gun sitting in the middle of a warming world. As the climate warmed at the end of the last glacial maximum, these giant lakes grew. The ice dams that held them back were never stable. They were more like temporary scars on a wounded landscape. Crevassed, fractured, constantly melting at the edges. But for thousands of years they held. Then, according to this hypothesis, they didn't. Imagine what happens when a dam fails. You don't get a gentle overflow. You get sudden, violent release, a wall of water racing downslope at highway speeds, ripping up forests, boulders, soil, anything in its way. Now scale that up from a reservoir to an inland sea thousands of kilometers across. When people talk about Lake Agassiz draining, the word is far too calm. We're talking about a catastrophic flood event, or more likely a series of them, as the lake found new outlets and new paths to the ocean. These are the famous meltwater pulses, sudden injections of fresh water into the world's oceans. For the younger Dryas, the critical part of the story is where that fresh water went. Most versions of the meltwater pulse theory focus on a catastrophic outburst of Lake Agassiz into the North Atlantic. The idea is simple but powerful. You take an entire continent's worth of fresh water, release it rapidly into the ocean, and you change how that ocean works. To see why, you have to understand that the Atlantic isn't just a big puddle, it's a machine. On the surface, warm salty water flows northward, carried by currents like the Gulf Stream. As that water moves toward higher latitudes, it cools. Cold water is denser, salty water is denser. Put those together, and in the right places the surface water becomes heavy enough to sink. That sinking drives what scientists call the Atlantic Meridional Overturning Circulation, or AMOC. You can think of it as a conveyor belt that moves heat around the planet. Warm water flows north at the surface, gives up its heat to the atmosphere, helping keep places like Western Europe far milder than their latitude would suggest. Then, cooled and dense, it sinks into the deep ocean and flows back south as a slow, cold undercurrent. This isn't a small local current. It's part of a planetary system often called the global conveyor belt. It helps regulate climate across hemispheres. Change it, and you change everything. Now imagine what happens if you dump a huge volume of cold, fresh water right where that conveyor belt is supposed to sink. Fresh water is less dense than salty water, less eager to sink. Pour enough of it into the North Atlantic and the surface layer becomes lighter, more buoyant. The dense, salty water that used to plunge downward suddenly struggles to do so. the engine that drives the overturning circulation stalls, or at least sputters badly. This is the key move in the meltwater pulse theory. No impact, no comet, just physics. Ice sheets melt, lakes fill, dams fail, freshwater floods into the Atlantic, amok weakens, and the climate snaps back to glacial conditions over large parts of the northern hemisphere. In this story, the younger Dryas isn't an alien intrusion from space. It's a feedback loop in Earth's own climate system, a kind of cold whiplash triggered by the way oceans respond to sudden freshwater loads. There's evidence that something like this can happen. In Greenland's ice, trapped air bubbles and layered snowfall record past climates in exquisite detail. When scientists drill deep into that ice and analyze the layers, they see rapid shifts in temperature linked to changes in ocean circulation, not just during the younger Dryas, but at other times in the last glacial period. Warm periods that ended abruptly, cold snaps that arrived in a human lifetime. In marine sediments on the floor of the North Atlantic, tiny fossils of plankton tell similar stories. Species that like warmer, saltier waters suddenly replaced by species adapted to colder, fresher conditions. Layers of ice-rafted debris, rocks carried by floating ice and dropped as it melts, hint at changes in where and how sea ice formed and drifted. There's also the geometry of the land itself. Around the former margins of Lake Agassiz and its sister lakes, geologists have mapped old shorelines, strand lines, and abandoned spillways, deep channels carved by ancient floods. They found huge deposits of gravel and sand laid down by catastrophic flows. In some places they can see abrupt drops in lake level, as if the water suddenly found a new escape route and drained away. In the North Atlantic and Arctic there are layers of freshwater-loving microfossils and changes in the chemistry of the sediments that suggest pulses of low salinity water entering the ocean. These have been dated to around the onset of the younger Dryas. Even far from the North Atlantic, rivers and deltas tell their own versions. Sudden changes in sediment load, shifts in where rivers entered the sea, floodplains cut and refilled. A global fingerprint of a world reorganizing its water. None of this is as dramatic as a comet explosion. There's no firestorm, no crater, no diamond-rich boundary layer you can point to and say, "Here, this was the day everything changed." Instead, the evidence for meltwater pulses is more like a quiet chorus of clues, scattered across the world, all humming the same tune. But how clean is that tune? How simple is the story? Even within the meltwater pulse framework, the details are messy. Exactly when did Lake Agassiz drain? Once, many times. Did the water go east into the St. Lawrence and the North Atlantic, or north into the Arctic Ocean, or south through the Mississippi Basin into the Gulf of Mexico? Different studies have suggested different routes at different times. Some reconstructions place the biggest outburst a bit before the younger Dryas. Others put it right at the beginning. Some argue for multiple pulses, a staggered staircase of releases rather than one catastrophic fall. And then there's the AMOC itself. Did it fully shut down, or just weaken? How sensitive is it to freshwater input? Modern climate models suggest it can be disrupted, but the exact thresholds are still debated. We're dealing with a chaotic system, not a simple on-off switch. Still, the broad picture remains compelling. A major freshwater event or series of events destabilizes the Atlantic circulation and plunges large parts of the northern hemisphere into a sudden severe cold spell. Forests retreat, ice sheets stop shrinking and start growing again. Glaciers advance. Species that had been moving north, tracking the warming climate, find themselves pushed back into refuges or wiped out entirely. When you lay this next to the impact hypothesis, you get an interesting question. Do we have to choose? A lot of scientific debates get framed as either or. Either a comet did it, or meltwater did it. Either fire from the sky, or floods from the ice. but the real world is rarely that clean. It's entirely possible, some researchers suggest, that both stories hold part of the truth. Imagine a large impact, or even a cluster of mid-sized ones, occurring over the Laurentide ice sheet or nearby. The explosion vaporizes ice, darkens the atmosphere with dust and soot, and ignites wildfires. At the same time, the shock waves and intense localized heating destabilize already fragile ice dams. Melt rates spike. Cracks propagate through the ice. A system already under stress tips over. In that scenario, the impact doesn't replace the meltwater pulses. It triggers or amplifies them, or flip the emphasis. Perhaps the primary cause of the younger Dryas was the internal dynamics of the climate system. The slow build-up of meltwater, the inevitable failure of ice dams, the collapse or weakening of the AMOC. In this version, if there was an impact, it was more of an unwelcome guest arriving at a party that was already going badly. Freshwater flooding into the North Atlantic could have made the climate system exquisitely sensitive. A relatively modest additional perturbation, dust, soot, or aerosols from an extraterrestrial event, might have pushed it that last crucial inch into a new, colder state. Or maybe there was no impact at all, and all of the strange evidence cited by impact proponents has other explanations. Natural wildfires, volcanic inputs, localized events preserved in a patchy record. In that case, the meltwater pulse theory stands alone as a complete explanation. Ice sheets, lakes, fresh water, currents, climate. For now, the jury is still out. What we can say is that the Earth at the end of the last ice age was not a stable place. It was a world in transition, an enormous creaking system shifting from a glacial state to something more like the present. Ice sheets were collapsing, sea levels were rising, ecosystems were migrating, humans and megafauna were moving into newly opened lands. In such a world, it doesn't take much to cause big changes. A few extra degrees of warmth, a bit more meltwater in the wrong place, a slightly weaker current, or perhaps something bright and fast crossing the night sky. The meltwater pulse. Theory reminds us that you don't always need a single dramatic villain. Sometimes the most powerful forces in history are quiet ones. Water pooling behind ice, salt mixing with fresh, a current turning more slowly in the deep. And sometimes the real story isn't one cause or another, but the way multiple threads braid together. Ice, ocean, atmosphere, life. Impacts from above, pressures from below. All woven into one long, complicated event we now call the Younger Dryas. While we sleep and imagine locked ice dams and rushing floods, deep in the past the oceans were already rearranging themselves, setting the stage for what came next. The disappearance of giants, the reshaping of human cultures, and the strange moment when our ancestors found themselves standing at a crossroads between worlds. Picture the continent under your feet, but strip away the highways and cities, the farms and suburbs. Replace them with herds so large they blur into the horizon. Mammoths and mastodons grinding ancient grasslands under their feet. Giant ground sloths as tall as a giraffe tearing branches from trees. Saber-toothed cats lying in the shade, muscles coiled. Short-faced bears towering over any human alive today. Camels, horses, giant beavers the size of black bears. An entire bestiary that feels half myth and half nightmare. Now imagine almost all of it gone. By the end of the Pleistocene, roughly around the Younger Dryas and the warming that followed, North America had lost about 35 genera of large mammals. Not just a few species here and there, whole lineages that had ruled the continent for millions of years. Mammoths, mastodons, North American camels, native horses, giant sloths, glyptodons with armored shells, the massive American lion, the terrifying short-faced bear, the dire wolf. One by one, they vanish from the fossil record. If you walked across the continent a few thousand years before this collapse, you'd have needed to watch every horizon, every thicket, listening for the rumble of herds or the low growl of predators. Walk that same path a few thousand years after, and the world would feel strangely empty. Deer, bison, elk, bears, yes. But the true giants, the ancient monarchs of the Ice Age, were gone. Why? This is the question that hangs over the younger Dryas like a ghost. Did a comet wipe them out? Did rapid climate change finally push them over the edge? Or was the real culprit something much smaller, much more recent? People with stone-tipped spears. The overkill hypothesis is a simple idea with disturbing implications. It says that when humans arrived in the Americas, probably around 16,000 years ago, perhaps a bit earlier, moving along coasts, river valleys, and ice-free corridors, they entered a world full of animals that had never seen them before. To mammoths and ground sloths, a small biped with a stick and a sharp stone didn't look like a super predator. It looked like nothing important at all. That miscalculation might have been fatal. According to the overkill model, as human populations spread south and east, they hunted the largest, slowest reproducing animals first. Big herbivores that lived in herds provided huge quantities of meat, bone, fat, and hide, and replaced themselves slowly. A mammoth cow might raise only a few surviving calves in a lifetime, lose too many adults too fast, and the population begins to slide. Add coordinated hunting, knowledge sharing, and maybe even drive techniques, pushing herds into bogs, ravines, or trap lines, and the slide can become a collapse. Supporters of this idea point to several clues. In many regions, the last fossils of Megafauna appear very close in time to the first clear evidence of widespread human presence. Some kill sites show mammoth bones associated with Clovis spear points, the distinctive fluted stones that appeared just before the younger Dryas. The pattern looks at first glance like a wavefront. Humans arrive, Megafauna disappear, and people didn't need to hunt everything for this to work. They only had to push already vulnerable populations below their replacement threshold. Just a slight increase in adult mortality. A few more cows lost each year than the calves coming up behind them. Over centuries, over a continent, small imbalances add up. But the story isn't that simple. When you look closely at the archaeological record, confirmed kill sites, places where we can be confident humans actually hunted and butchered megafauna, are surprisingly rare. Clovis points are common, but mammoth skeletons with embedded weapons are not. Many megafauna vanish at slightly different times in different regions, and some Ice Age giants survived human contact for thousands of years elsewhere in the world. If humans alone were a planetary extinction machine, why weren't they equally deadly everywhere all at once? That's where climate enters the story. The end of the last Ice Age was not a gentle, gradual thaw. It was a roller coaster. Between roughly 18,000 and 11,700 years ago, ice sheets retreated, then stalled, then surged. Sea levels rose. Vegetation zones shifted northward, then snapped back. And then, right in the middle of this chaotic transition, came the younger Dryas, a sudden plunge back into near-glacial conditions that lasted more than 1,000 years. Megafauna had survived climate swings before. They had endured cold stadials and brief warm interludes over hundreds of thousands of years. But the late Pleistocene was different in two crucial ways. First, the pace of change seems to have been faster, especially at regional scales. As ice sheets melted, they disrupted ocean currents, altered rainfall patterns, and remapped entire ecosystems. Grasslands became shrublands, forests marched into former steppe, wetlands drained, or flooded, or shifted. Animals adapted to wide, open, icy plains found themselves living in patchy mosaics of forest and marsh. The buffet table they had known for millennia was being cleared away. Second, And more importantly, this time the climate upheaval did not happen in an empty world. It unfolded in a landscape where a new kind of predator was learning, adapting, and sharing knowledge at unprecedented speed. Under the climate change hypothesis, many megafauna populations were already stressed before the final crash. As habitats fragmented, herds had to move farther to find food. Winters might have become drier or longer in some regions, summers hotter or less predictable in others. Droughts and late frost could damage the plants they relied on. Calves and juveniles would be the first to suffer. Birth rates drop, body condition declines. Diseases spread more easily through weakened herds. Then the younger Dryas hits. Temperatures plunge in just a few decades in some areas. Vegetation shifts again, pushing ecosystems into new configurations. For species that need vast ranges, mammoths roaming across steppe tundra, horses grazing endless grasslands, the world shrinks into scattered patches of suitable habitat. Populations that were already reduced by millennia of warming find themselves pushed into climatic bottlenecks. In that world, a relatively small number of motivated human hunters can have outsized effects. They don't need to be perfect. They don't need to kill every mammoth or every sloth. They only need to add one more pressure to a system already wobbling. This is where the younger Dryas becomes less a single cause and more like the last heavy stone added to an overloaded cart. If there was an impact, a comet or fragmented meteor shower as some researchers suggest, it might have started fires, injected dust, altered atmospheric chemistry. Even if it didn't, the abrupt cooling itself, with or without a cosmic trigger, would have torn at already fragile ecosystems. Imagine a mammoth population living at the edge of its climatic tolerance. Warmth has reduced its ideal habitat, fragmented it. The animals must move farther between patches of good grazing. Calves struggle in lean years. Then a sharp cooling snaps the plant communities again, changing snow patterns, freezing wetlands, replacing certain grasses with others. The mammoths can't simply teleport to better lands. They have to move through territories already occupied by other herds, by predators, and now by humans. Every migration route becomes a gauntlet. While this drama was playing out in North America, other parts of the world tell a slightly different story. That's one of the most important clues. In Africa, many large mammals survived the end of the Ice Age. Elephants, rhinos, hippos, giraffes, buffalo. In parts of Asia too, some megafauna endure. Even in South America, though the losses are severe, a few giants make it longer. Why? One possibility is time. In Africa especially, large mammals had been living alongside increasingly capable human hunters for hundreds of thousands of years. They had the evolutionary equivalent of a long, drawn-out negotiation with us. Natural selection had time to favour individuals who learned to avoid human hunters, shifted their activity patterns, changed their behaviours. Humans, in turn, adapted to these evasive strategies, but the arms race played out over a long enough span that it didn't end in complete collapse. In the Americas, by contrast, the meeting between humans and megafauna was abrupt. Herbivores and predators there had never seen a hominin, never watched a primate cooperate in coordinated drives, never experienced long-range projectiles that could kill from beyond the reach of hooves, tusks, or claws. They met humans at a time when climates were already unstable. There was no long co-evolutionary dance, no slow escalation of caution and counter-strategy. There was only impact. Regional climate patterns also differed. The way ice sheets melted in North America, the way ocean currents rerouted, the timing of vegetation shifts. All of this created local pressures that might have been harsher for certain species than anything they faced elsewhere. Some refugees vanished entirely. Others shrank to postage stamps. Yet even within North America, the pattern isn't uniform. Bison survive, though the largest forms disappear. Some deer, elk, smaller predators, and scavengers persist and even thrive in the new Holocene world. This suggests the extinction wasn't a simple blanket event. It was a selective filter, biased against animals that were big, slow-breeding, specialized in their diets, or poorly adapted to rapid environmental change. When those animals disappeared, the effects rippled outward through entire ecosystems. Predator-prey relationships that had stabilized over millennia were suddenly broken. Saber-toothed cats and American lions lost their primary prey. Short-faced bears, which may have relied heavily on scavenging megafaunal carcasses, lost their food base. Their own extinctions became part of a cascading collapse. On the plant side, the loss of large herbivores changed fire regimes, seed dispersal, and nutrient cycling. Mammoths had been ecosystem engineers, knocking over trees, trampling shrubs, maintaining open grasslands. Without them, forests invaded former steppe. This, in turn, altered habitats for birds, small mammals, insects, and even the humans who followed. In that sense, the megafauna extinction was not just the disappearance of impressive animals, it was a rewiring of the entire continent, a quiet revolution in how energy, matter, and life flowed through the landscape. The world after the Younger Dryas was not just emptier, it was fundamentally different. So what caused it? Most researchers today lean away from single-cause explanations. Pure overkill, humans alone, seems too simple, given the regional differences and the timing. Pure climate, with humans as innocent bystanders, also feels incomplete, given that similar or even harsher climate swings in earlier ages did not wipe out megafauna on this scale, while humans were conveniently absent. The emerging picture is more complex and in some ways more unsettling. Climate change likely weakened many populations first, fragmenting their habitats and reducing their numbers. The Younger Dryas, however it was triggered, intensified that stress. Then humans arrived, or increased in number and efficiency, and applied the final pressure. Targeted hunting of the largest, slowest reproducing animals, disruption of migration routes, perhaps competition for key water sources and grazing grounds. In some regions, climate may have been the primary driver, with human hunting only accelerating an already downward trend. In others, human overkill might have been decisive, with climate providing the background stress. Predators like saber-toothed cats and dire wolves may have slipped away mainly because their prey did. Scavengers followed. Plants shifted in response to the new herbivore regime. The whole system tipped into a new stable state. In this view, the megafauna were not simply victims of a comet or a cold snap or a wave of spear-wielding hunters. They were caught at the intersection of all three: long-term warming, abrupt cooling, and the arrival of a clever, adaptable, highly cooperative primate whose numbers were rising. And that primate, of course, was us. We don't know every detail. Debates continue about the exact timing of each disappearance, the number of humans on each landscape, the severity and causes of the Younger Dryas cooling. Some researchers still argue for a major role for cosmic impacts. Others see them as unnecessary. But beneath the disagreements, a broad pattern is taking shape. Extinctions of this magnitude rarely have a single cause. They arise when multiple pressures align: climate volatility, habitat disruption, new predators, disease, perhaps even chance. For the mammoths and their companions, the late Pleistocene provided all of these at once. When you stand in a museum today, looking up at the towering skeleton of a mastodon, or trace the curve of a mammoth tusk with your eyes, you're seeing more than just bones. You're seeing the echo of a vanished world, a world that blinked out in the same turbulent age that gave rise to our own global story. And as the Younger Dryas ended, and the ice retreated for the last time, the empty niches those giants left behind did not stay empty for long. Another large mammal, far smaller in body but far more flexible in mind, was already spreading into the spaces they had once owned. Humans were stepping into a quieter but no less dangerous world, and the cultures they built in the shadow of that extinction would carry the memory of the lost giants in stories, symbols, and perhaps in the shapes of their tools. The age of mammoths was over. The age of humans had truly begun. Imagine North America about 13,000 years ago, right before the younger Dryas hits its stride. You're standing on the edge of a broad, cold plain. Not quite tundra, not quite grassland. The ice sheets have pulled back, but not by much. To the north, walls of ice still glint on the horizon. To the south, scattered forests, wetlands, and open steppe stretch away for hundreds of miles. And moving across that landscape, almost ghost-like, are small bands of humans carrying a very particular kind of technology. Long, elegant stone spear points, shaped with such skill that they look almost modern. Thin, symmetrical, with a distinctive groove, or flute, chipped out from the base on one or both sides. Tools so sharp they could skin a mammoth or cut through bone. So standardized you can recognize them in an instant. Archaeologists call this toolkit Clovis. For decades, Clovis was treated like the opening act of human history in the Americas. The first people, the first hunters, the first culture to leave a clear, widespread footprint across the continent. From New Mexico to Nova Scotia, from the Great Plains to the southeast, Clovis points appear like a signature carved into stone, and then, very suddenly, that signature fades. Around the time the younger Dryas begins, the classic Clovis toolkit disappears from the archaeological record. Those fluted points, the hallmark of Clovis, stop showing up in new layers of sediment. The campsites change, the tools change, the patterns of movement change. It's as if the continent turned a page and the word Clovis was no longer written on it. For a long time, that disappearance looked like a mystery, a culture with the most advanced hunting weapons of its day, spread over thousands of miles, gone in what seems like an archaeological instant. Did they die out? Were they wiped away by a comet, by wildfires, by sudden cold? Or did something more subtle happen? To understand that, you have to slow down, breathe with the rhythm of archaeological time, and look not just at what vanished, but at what came next. Because the end of Clovis is not the end of people. It's the end of one way of being people in a world that was changing fast. As the younger Dryas cold snaps into place, new tool traditions begin to appear in the layers above the last Clovis points. In the east, you see something called gainy, or bullbrook in New England, and related variants across the Great Lakes region. In the west, you start to see Folsom, with its own beautifully fluted points, thinner and more delicate than Clovis, tuned not for mammoth, but for bison. Instead of one overwhelmingly dominant style like Clovis, the archaeological record fragments into a patchwork of regional cultures, different groups experimenting with different solutions to the same problem, how to stay alive when the climate system itself is lurching and stumbling. This pattern, one big widespread toolkit giving way to many localized ones, is exactly what you'd expect in a world where conditions are unstable and resources patchy. Under the relative warmth of the period just before the younger Dryas, big game like mammoth, mastodon, and huge Pleistocene bison would have been more common across broad swathes of the landscape. A high-mobility hunting strategy with long-range weapons designed for taking down large animals made sense. When the cold returned, brutally and quickly, those herds shifted, fragmented, shrank. Some disappeared entirely from certain regions. The food landscape became more complicated. Hunters could no longer rely on the same animals in the same places season after season. So the people changed. Folsom hunters in the plains refined their points for smaller, quicker, more agile bison. In the east, some groups turned more towards smaller game, fish, and plant foods. In the west, on the coast, people leaned harder into marine resources. Everywhere you see signs of flexibility, of improvisation, of cultures refusing to stand still while the world rearranged itself. From a distance, it can look like Clovis disappears. Up close, it looks less like extinction and more like transformation. A broad, continent-spanning way of life breaking apart into regional strategies, each adapted to local climates and local opportunities. But adaptation doesn't mean the process was gentle. There are hints that population numbers may have fallen, at least in some regions. Sites that were busy with many layers of occupation suddenly go quiet. Places that show dense activity before the younger Dryas show only scattered visits, or none at all during the coldest centuries. On the Great Plains, some areas that were once rich hunting grounds seem to have been abandoned or used only seasonally. In parts of the northeast, the archaeological record thins out. You go from clusters of campsites to isolated finds, a lost spear point here, a broken tool there, as if the people who used to live there had pulled back to more reliable refuges. If you imagine yourself as one of those people, the decision to leave is not abstract. It's the realization, year after year, that the rivers you depended on are frozen longer, that the herds pass less often, that the plants you gathered bloom late or not at all. It's watching a territory that once fed your grandparents become a place of hunger, and then it's a council fire, quiet discussions, the decision to move, to follow the animals, to seek better fishing, to join distant kin. So while Clovis as a distinctive technology fades, the human story continues, sometimes with fewer voices in certain regions, sometimes with entire valleys going silent. The younger Dryas didn't just take mammoths. It very likely rearranged human populations, forced migrations, culled some lineages and privileged others. And yet the picture is not simply one of collapse and flight. In some places, people stayed. There are sites that show continuous human presence right through the younger Dryas cold. In the American West, places like the Paisley Caves in Oregon, or sites in the Great Basin and along the Pacific coast, hold layers that run from before the cold period into its heart and out the other side. The tools change gradually, but the presence remains. Hearths are rebuilt, bones pile up, shell middens grow thicker. Fire-cracked rock testifies to thousands of meals cooked in the same places. These are not the signatures of a continent utterly emptied by disaster. They are the traces of communities that bent without breaking. In the southeast, along river valleys and coastal plains, there's evidence of continued occupation as well. The focus of subsistence shifts. More fish, more shellfish, more small game, but the campsites stay occupied. People learn which river mouths freeze least, which wetlands hold water even in drought, which groves of nut-bearing trees can be relied on when other foods fail. Taken together, the record shows a continent that did not simply lose its people, but repatterned them. Some groups may have vanished entirely, others shrank and survived by the narrowest margins. Still others found ways to thrive in ecological niches that suddenly mattered more than ever. And while this is happening in the Americas, a different but parallel drama is unfolding in the Near East, around the same time that Clovis hunters are watching their world change. Groups in the Levant, places like Natufian sites in what is now Israel, Jordan and Syria, are living through the younger Dryas in their own way. Just before the cold sets in, these Natufian communities show something remarkable. Increasing sedentism. People are starting to stay in one place for much of the year. They build more substantial houses. They harvest wild cereals like wheat and barley. They use grinding stones to process seeds and grains. It's not quite agriculture, not yet, but it's close. Then the younger Dryas hits the eastern Mediterranean. Rainfall patterns change. Wild cereals become less predictable. the environment that had supported semi-sedentary foragers becomes harsher, more erratic. For a time, it looks as if this first experiment in settled life might reverse. Some Natufian groups seem to go back to more mobile strategies, moving more often, ranging more widely to find food. Villages shrink or are abandoned, and yet the memory of what they had been doing, the knowledge of plants, of seasons, of harvest and storage, doesn't vanish. It lingers in the people, in their tools, in their stories. When the Younger Dryas finally ends, around 11,700 years ago, the climate in the Near East becomes warmer and wetter again. The wild cereals recover, but now there are people in the landscape who already know their secrets. That's when you see something new. Deliberate planting, tending, and eventually domestication. Wheat and barley that no longer scatter their seeds on their own, but hold them until harvested. Settlements that grow larger and more permanent. Storage pits. The first glimmers of what we would recognize as agriculture. In this sense, the Younger Dryas may have acted as both brake and catalyst. It interrupted a gentle drift towards settled life, forcing Natufian societies to confront the limits of simple foraging in an unstable world. At the same time, it preserved and concentrated the knowledge they had gathered, so that when the climate improved, the leap into farming happened relatively quickly. The cold didn't create agriculture by itself, but it may have sharpened the question that agriculture ultimately answered. How do you hold on to security in a world that keeps taking it away? Seen across the globe, the Younger Dryas looks less like a single catastrophe and more like a series of crossroads, repeated in different places with different outcomes. In North America, it marks the transition from a big game-dominated Clovis-style hunting world to a mosaic of regional cultures, each tuning itself to local conditions. In the Near East, it sits between two phases of experimentation, early sedentism and full-scale farming. Everywhere, you see the same underlying pattern: stress, contraction, experimentation, and then, when conditions allow, expansion into new forms of life. The debates about what triggered the Younger Dryas, Comet, meltwater, shifting currents, are important. But for understanding human history, what matters just as much is what people did with the situation they found themselves in. They didn't simply endure it passively. They adjusted their tools, their diets, their settlement patterns, their social networks. They abandoned some places and clung to others. They preserved knowledge through generations that never knew stability. Think back to those Clovis hunters again, standing on the edge of receding ice, holding their flawless fluted points. Their descendants, genetic and cultural, would one day become buffalo hunters on the plains, salmon fishers on the Pacific coast, maize farmers in Mesoamerica, city builders in the Mississippi Valley. None of that was inevitable. It depended on thousands of small decisions taken under pressure in a world that refused to stay the same. The same is true for the Natufian villagers grinding wild grain on stone slabs. Their children's children would plant fields that fed the first cities of Mesopotamia. Again, not as destiny, but as a fragile thread of choices, held together through droughts, frosts, and long winters. When you look at the Younger Dryas this way, the focus shifts. It stops being just a mystery about climate graphs and possible impacts, and becomes part of a much older, deeper story. The story of a species that has lived for hundreds of thousands of years, with the knowledge that tomorrow's world may not look like today's. The end of Clovis is not a disappearance so much as a hinge. On one side, a world of giant mammals, of ice and open plains, of hunters following herds across unmarked continents. On the other side, a world of regional traditions, diversified diets, increasingly complex social networks, and, in the Near East, the first cautious steps toward farming. Between those worlds lies a sudden cold snap, a climate gone wild, and millions of individual acts of resilience. Every fluted point left in the ground, every abandoned campsite, every village that held on through the worst winters is a record of those acts, of people who refused to give up even when the seasons themselves seemed to turn against them. We live at the far end of those choices now, in a world shaped by agriculture, cities, and centuries of technological change. But in our bones and in our stories, we still carry the memory of the younger Dryas, a time when humans stood at crossroads, watched the climate break, and once again found ways not just to survive, but to begin something new. Picture the scene now, not 12,000 years ago, but this morning. Fluorescent lights humming in a lab, a graduate student hunched over a microscope, eyes aching, searching for something that looks like a tiny diamond, or a melt glass droplet, or a microscopic sphere of metal that shouldn't be there. On a computer nearby, someone else is running climate models, watching coloured bands of temperature slide back and forth across a virtual Earth. In another building, a radio telescope is listening for faint whispers from rocks drifting silently through space. This is where the younger Dryas lives today. Not in a crater you can walk around, not in a single smoking gun. It lives in graphs and sediment cores and arguments over email. It lives in conferences where someone stands up and says, "I think you're wrong," and then backs it up with 40 new pages of data. If you zoom out, what you see isn't a settled story. You see a work in progress. Right now, most scientists agree on a few basic things. The younger Dryas was real. It was abrupt. In Greenland ice cores, you can trace it almost like a cliff edge. One layer, things are warming as the last ice age relaxes its grip. The next, temperatures plunge. Within a human lifetime, maybe within a few years. Something dramatic happened to Earth's climate system. They also agree that around the same time North America's giant animals vanished. Mammoths, mastodons, giant ground sloths, saber-toothed cats. Some lingered in scattered refuges, but the ecological tapestry that had covered the continent for tens of thousands of years unravelled in the space of a few centuries, maybe less. And they agree that human cultures changed. The Clovis toolkit, with its elegant fluted spear points, fades out. New styles and strategies appear. Different weapons, different ways of living in a changing world. The disagreement is about the hammer that hit the system. Was it ice? Was it water? Was it us? Or was it something from space? In the early years after the younger Dryas impact hypothesis was first proposed, the field split hard. Some researchers were intrigued, even excited. Others were openly hostile. Papers came out fast, data flying in both directions. There were accusations of sloppy methods, of cherry-picked evidence, of overblown claims. It felt at times less like science and more like a courtroom drama. But time has a way of sanding off the sharpest edges. Today, the debate looks different, calmer, more precise, less about impact or no impact, more about how much, where, and what exactly did it do. Over the last decade, a steady trickle of new studies has complicated the picture. Some support parts of the impact idea, some undercut it. Some suggest hybrid scenarios where multiple forces interact. In Greenland and Antarctic ice, researchers have found unusual spikes of platinum and other trace elements around the start of the younger Dryas. Platinum is rare in Earth's crust, but more common in some types of meteorites. That doesn't prove a cometary impact, but it nudges the probability in that direction. It whispers, something metallic, something extraterrestrial might have been involved. In lake sediments and soil layers across Europe, North America, and parts of the Middle East, other teams have reported peaks of tiny magnetic spherules, soot and carbon-rich layers that look like the residue of large-scale burning. They've found microscopic diamonds and glass-like particles that form at very high pressures and temperatures. Some of these studies line up neatly with the timing of the Younger Dryas onset. But for every data set that seems to support a cosmic trigger, there is another that raises questions. Several groups have tried to replicate these findings and come up empty. Same layers, different labs, no diamonds, or different concentrations, or signals that can be explained by local fires, volcanic dust, or slow, ordinary processes stretched out over centuries instead of minutes. Some sites once held up as impact smoking guns have been reinterpreted. Features thought to be blast effects from a cosmic explosion now look more like products of ice sheets melting, rivers reshaping their channels, or wind scouring loose sediments over thousands of years. Instead of a simple yes or no, the scientific literature has become a patchwork. Some cores show unusual signals, others don't. Some regions display evidence of synchronous burning. Others appear quiet. The planet, it seems, rarely gives us a clean experiment. So where does that leave things? If you listen to researchers talk today, you won't hear many extreme positions. Few are willing to declare the impact idea completely dead. Few are comfortable embracing it as the main driver of the Younger Dryas without reservation. The centre of gravity has shifted toward a narrow, cautious middle. One camp sees the Younger Dryas impact hypothesis as unlikely in its strong form but intriguing in its weaker variants. Maybe there was no single massive airburst that wiped out forests from coast to coast, but perhaps smaller fragments did hit ice sheets or oceans, contributing extra chaos to an already unstable system. Not the cause of the Younger Dryas, but a nudge that made a bad situation worse. Another camp thinks we don't need space rocks at all. They argue that meltwater pulses from collapsing ice dams, changes in ocean circulation, shifts in atmospheric patterns, and human hunting pressure together can explain the climate reversal, the megafauna decline, and the cultural transitions. From this perspective, adding a cosmic impact isn't necessary. That doesn't mean it didn't happen, just that the burden of proof remains high. Between these poles sits a large group that might be described as cautiously agnostic. They follow the new data. They run new models. They keep an open mind but demand tight methods, clear stratigraphy, and independent replication. They're willing to be convinced, but not by a single layer of black dust or a handful of unusual grains. What's changing the debate isn't just more data, it's better tools. New dating techniques are narrowing the uncertainty windows around key events. Radiocarbon calibration curves are being refined. Optically stimulated luminescence methods are improving, letting researchers pin down when sediments were last exposed to sunlight. This is crucial, because to argue for a causal link, timing has to line up very tightly. The more precise the clocks, the clearer the sequence becomes. High-resolution climate models are also getting better. They can now simulate how ice sheets, ocean currents, and atmospheric circulation might have responded to sudden pulses of meltwater or abrupt shifts in solar input. Some teams have run scenarios where a large impact injects dust and water vapor into the atmosphere, or vaporizes parts of an ice sheet. The models ask, what would that do to the North Atlantic, to the jet stream, to the monsoons? Early results suggest that a big enough disturbance could, in theory, trigger something like the Younger Dryas, but in theory is not the same as in fact. On the forensic side, analytical chemistry is reaching down to finer and finer scales. Instruments can now measure trace elements and isotopes in tiny particles with extraordinary precision. They can distinguish between platinum that likely came from volcanic sources and platinum with a signature more typical of meteorites. They can tell whether a diamond formed deep in Earth's mantle or in a brief moment of shock and heat near the surface. Space technology is also quietly entering the story. Surveys of near-Earth objects are cataloguing comets and asteroids with increasing completeness. By tracing their orbits backward, some teams are exploring whether any known families of debris could have intersected Earth's path around the time of the Younger Dryas. So far, no smoking comet has appeared with a sign around its neck reading, "I did it," but the search continues. Imagine, a century from now, a different kind of evidence. Maybe an ice core pulled from a part of Greenland we haven't drilled yet, showing a thin layer enriched in specific isotopes that can only be produced in high-energy atmospheric explosions. Or a buried crater under an old ice margin, found by ground-penetrating radar, its age pinned down to within a few centuries of the younger Dryas onset. Or perhaps instead, a seamless, globally consistent record of gradual changes leading into the cooling, with no sharp disturbance at all. These are the kinds of discoveries that could finally push the debate toward a consensus. Not arguments, not hunches, but clean, converging signals from multiple independent lines of evidence. But until then, the younger Dryas sits in a liminal space, not myth, not solved, not forgotten. There's a larger story hiding inside this argument. It's about how fragile Earth systems can be and how small the triggers sometimes are. A shift in ocean salinity, a change in where ice melts, a perturbation in atmospheric circulation, perhaps a fragment from space, crossing our orbit at precisely the wrong moment. We live on a planet that has been hit before. The scars are written into the rocks, into the fossil record, into the sudden disappearances of entire lineages. The younger Dryas debate, whether or not a comet was involved, reminds us that climate is not a gentle linear background. It can flip, it can lurch, it can enter new states in less time than it takes a great-grandparent to be born and die. Modern surveys scan the skies now, cataloguing threats. Algorithms estimate impact probabilities. Engineers draw up contingency plans. But even with all of that, uncertainties remain. Small objects can arrive with little warning. Large ones are rare but not impossible. The Earth is not a sealed bubble. It's a target moving through a shooting gallery of cosmic debris. Thinking about the younger Dryas, about mammoths in a snowstorm and Clovis hunters on a cold morning, you can feel that vulnerability reach backward. Were they struck by something they could never have imagined? Or were they simply caught at the intersection of ice, water, and human ingenuity as a warming planet stumbled and then recovered? Science may yet answer that, or it may not, at least not soon. One of the quiet lessons of this mystery is about how knowledge grows. It rarely arrives as a single revelation. It accumulates, layer by layer, like sediment settling at the bottom of a lake. A new method is developed, an old sample is reanalyzed. A forgotten core in a museum basement yields a surprise. A theory rises, gathers support, then is shaved down, refined, sometimes overturned, sometimes reborn in a more modest form. Researchers argue, but beneath the argument is a shared process. Hypotheses are proposed, tested, criticized, defended, modified. Failed ideas are not wasted.